So good morning, everybody. Okay, we come back to the very basic question about the nature of mass. So we start with the same big question Ivette started yesterday. What is mass? Is mass a form of energy, or is it something fundamentally different? That's our key question. Before going to the quantum phenomena and double-slit experiment discussions, I like to remind the basic meaning of mass in the build-up of universe, in the dynamic universe thing. But let's look what is the classical definition of mass. Mass is a measure of inertia. Mass was assumed to conserve, and also mass expresses gravitation. Modern physics defines the properties of mass as inertial mass, which means resistance to acceleration, in the same way, more or less in the same way as in classical physics. Gravitational mass, which is related to the space-time curvature, and inertial mass is assumed to be equal with gravitational mass, which is one form of expressing the equivalence principle. So in modern physics, mass is considered a form of energy, in spite of the fact that mass is measured in kilograms and energy is measured in joules. Also, rest mass is considered as an invariant. How about in DU? The basic things is mass is considered and described as an energy carrier or substrate for expressing energy, and respecting the dimensional analysis. So the joules energy is measured in joules, and kilogram is a part of expressing energy. Further, we are then looking how mass is able to express electromagnetic energy. Generally, photons are considered as massless particles. So what is the role of mass in photons? Also, what is a mass particle? In DU framework, we can find that mass is not necessarily presented only as a particle. And then what is the linkage of mass to the Compton wave, the De Broglie wave, and the wave function? Very important, as we discussed yesterday, inertia is a consequence of the zero energy balance in space. It's not a property of mass. So now we come to the very basic question, showing the essence of mass in presenting energy. So I repeat the picture we looked yesterday. We can see that the energy was built through a conversion of gravitational energy into the energy of motion. But what is also, at the same time, we can find here that in the total development of space, we can say that energy is built up and released, but mass is conserved throughout the whole development. And we wanted to show this just to pay attention to the very basic role of mass and the conservation of mass. So let's go to the key question in getting into the concepts of quantum and mass particles. How does mass express electromagnetic energy? So we start from the physical message of Planck's equation. We are used to express Planck's equation in form E is equal to h times f. Equally, we can express the equation in form E is equal h divided by t, where t is the cycle time 1 divided by f. And when using this expression, we can also conclude that physically this form can be interpreted as the energy emitted into on or carried by a cycle of radiation. So it gives a kind of physical explanation what is the package, energy package in a quantum of energy. So let's see what's the minimum amount of electromagnetic energy, electromagnetic radiation emitted by an antenna into one cycle of electromagnetic radiation. So this is a very standard formulation of the power emitted by a dipole antenna. We can find this equation from every physics textbook. And the only thing we need here is a little bit pay attention to the expression of the different quantities. So this is the dipole moment. N is the number of electrons, electron charge, and then Z0 is the dipole length. Also, we need to convert the angular frequency to frequency and wavelength in the suitable sense in order to make the solution into suitable form. It's very important also to understand, to find out that we need to use magnetic constant, the vacuum permeability, instead of permittivity, epsilon naught. So let's see how it looks, the solution here. So we like, as radio engineers do, we like to relate the dipole length to the wavelength emitted here. So here is the property of the antenna. And then in normal Hertzian dipole, we have a geometrical factor, 2 divided by 3, 2/3, and then we can find out a connection where we have electric charge, vacuum permeability, the velocity of light, and f to the second. So this is the power emitted, but we are interested the energy emitted a single cycle of electromagnetic radiation. So from that we need to multiply that with the cycle time or divide that by frequency, and while doing that we can find out that the energy emitted into one cycle of electromagnetic radiation here is the number of electrons to the second power. Then we have the dipole length related to the wavelength emitted to the second power here, then the geometrical factor of the antenna, and then constants 2 times p to the third, electric charge to the second, vacuum permeability, and the velocity of light here as a factor, and then frequency. We can find out that the dimensions of this part of the equations is kilograms times meter to the second divided by second, which is the dimension of Planck constant. Let's see. Now we make the choice. We look the minimum energy by setting n to 1, and we relate the dipole length to the emission wavelength, make it equal. So this is 1, 1, and we choose the geometrical factor be close to 1, representing a kind of isotropic antenna, and we get by choosing A equal to to 1.1049, we get exactly the Planck constant here. The important message here is that we have the velocity of light included in the Planck constant when it's related now to the electric constant, charge and vacuum permeability. So let's see how the equation looks like if we remove the velocity of light from the Planck constant. We call that the intrinsic Planck constant. And then the Planck equation can be written in different forms here. Instead of h, we have h0 times c times f. And when we turn express f as c divided by lambda, we get h0 divided by lambda times c to the second, or also we can use the wave number and reduced Planck constant, intrinsic reduced Planck constant, and we can find out that this quantity here has the dimension of kilograms, as well as this one are kilograms, and we get exactly the same form of energy as what we have for the rest energy or mass. Let's continue here. So, other way around, the definition of Compton wavelength. Compton wavelength is Planck constant divided by mc. Now it can be expressed as h0 by m, which means that we can express the energy mc to the second as h0 by the Compton wavelength, which is the mass, the wave expression of mass times c to the second. What is still extremely interesting here is that now, using the h0, or in fact we don't have even that, we don't need even that, but simply applying the Planck constant expressed in forms of the electrical constant, we can find out that the fine structure constant becomes a pure numerical factor or geometrical factor without any connections to other physical constant. So let's summarize. We have the intrinsic Planck constant, which is h0, which is h divided by c, or then the reduced intrinsic Planck constant. The Planck equation can now be expressed in forms of mass times velocity of light to the second, h0 divided by lambda, which are kilograms, times c to the second, h0 reduced times the wave number, which times c to the second gives the same equation. And very important conclusion here is that the Planck equation E is HF describes the emission or absorption conversion. It's not an intrinsic property of radiation. And this is extremely important conclusion also when interpreting cosmological predictions and the effect of redshift on the energy of propagating light. Now, applying the intrinsic Planck constant, we can now express the different energies, the energy of mass m, the unit cycle of radiation, even the Coulomb energy. Here we can express that using mu naught without any other new ideas. This is kilograms times c to the second, or c0 times c, where we make the distinction according to the dynamic universe framework. In the dynamic universe work, we have the number of charges here and fine structure constants times h0 divided by 2p rr times c to the second. So it's in the form, can be expressed in the form mc to the second as well. So we have a unified expression of energy. Also, we can find out that now we can follow the mass as the energy carrier here. We have the total energy of motion of a mass object here, and we can express that as C0 m plus delta m plus c. And now, if we are accelerating our system, we can also follow the conservation of energy. So the increased energy, increased mass, is not the consequence of the velocity, but it's exactly the mass energy carrier which we have removed from the accelerating system to the object accelerated. So it demonstrates the very effective way of following the conservation of mass in these conversions. So let's go then to a mass particle. Particle following the role of Compton wavelength. We can describe a mass particle as a Compton wave resonator, and from that we can find out that we can also find the connection to De Broglie wave. Here we are. So we describe a particle with basically it's a spherical structure in 3 dimensions, but for simplicity now we look that in 1 dimension. We can find out that the momentum in space directions is 0 because the resonator is built up of opposite waves forming standing waves, and the momentum now appears in the 4th dimension only. When we put the particle into motion, the Compton wavelength is increased, which is corresponds to time dilation effect in relativity theory, and in the DU framework we can see as a part of the energy of the zero energy balance. Motion reduces the rest mass, which is observed as increase of the Compton wavelength. Experimentally, that can be immediately observed. We know that particles in motion, that the emitting particles emit increased wavelength. So the emission wavelength is directly proportional to the Compton wavelength. So that it tells, without any relativity theory, we can conclude then that the Compton wavelength is increased. But what is still even more important here is that when the particle is in motion, then what we observe in the rest frame of the rest frame where the motion occurs, we can find out that the front wave wavelength of the front wave decreases, and the back wave of the resonator increases due to the Doppler effect. And expressing this as a momentum, we can see that the 2 observed waves have different momentum, and the net momentum as the sum of these two gives the wave carrying the momentum of the particle. And the first form here, this is exactly the De Broglie wave here, which has the velocity, when it's studied as a wave propagating at velocity c, or with the other wave number or wavelength as a wave propagating at the velocity of the moving particle. And both these expressions leads, when we convert, express the h0 by lambda with mass, we find that the momentum here, momentum wave carries the momentum rest mass of the particle at rest, divided by square root of v divided by c to the second, which is exactly the expression of the momentum in special relativity also. We now let this package, which includes the particle itself and the momentum wave, which follows the particle as a wavefront, we let it pass the double slit. The straightforward interpretation of that is that the De Broglie wave, or the momentum, which now has physical meaning as the momentum wave. Momentum wave passes through both slides, and the particle itself passes one of the slides, and then forms the interference pattern. So this is my, let's say, naive explanation of the double slit experiment, and let's see how it compares now to the Bohm ideas. First, we look basically the interference, the build-up of interference is something like this, so that the interference maximums comes here, but also they are effective from each of the slides. And now in the first phase here, let's assume that we have equal electron flux through both slits. I tried to include the Bohmian trajectories here. And also, if you pay attention, I try to apply your dimensions here so that we roughly know where we are going. And if I remember correctly, your acceleration voltage was something like 100 kilovolts. So that was it? Yes. Because we have another example here. But now let's make several following additions here. What happens? Yeah, this is now I remove the first trajectories. We have the Bohm trajectories, and we choose one here. If we choose at the same corresponding trajectory with my first light, we find out that here everything goes about the same, but here we met another maximum. Then let's follow. What do you think? Would there be any experimental way of checking what happens middle between, where we can find that the behavior of these two trajectories are about the same? But then next, let's see what happens if the electrons passes only through the upper slit here. So basically wavefront explanation, the situation is not very much different. But if we now add the Bohmian explanation, it meant that, or I must give the question to you, is that the correct interpretation? No.
There's only one slit open.
Yeah, through upper, that electron passes through upper slit, but this is open, the other is open.
Yeah, that would be correct.
Yeah.
Both slits are open.
Yeah. So the big question is that is the interference pattern now only on the upper side of the middle line here?
Well, the problem is you can't control through which slit the electron goes.
Yeah, so I don't have any opinion or. So I'm just trying to figure out, is there an experimental way of finding out the solution? Okay, because let's go further. So this is just a demonstration. So both slits are open, but electrons passes only through the one, and then here and these two. So basically, this is about the same as what we saw. But now Petri found an interesting report of experiment with asymmetric double slit by using a very high acceleration voltage, and that's made in field emission transmission electron microscope. So here the observation here was that the key empirical findings show that fringe visibility decreases proportionally with illumination asymmetry, and that complete loss of interference can occur even with both slits open when beam asymmetry is extreme. So here now we have electrons only passing the left-hand side beam through the left slit. Both slits are open. And we can see that there's some interference patterns which is quite different what comes then when the both beam through both slits. And here we can now see the higher frequency interference pattern. And this is very interesting also when I check with this high voltage, we have the De Broglie wavelength is much shorter than the Compton wavelength, and I check roughly the ratio corresponds to these differences here. I don't know whether that's what physical things that happens. It was just an observation, and it's extremely interesting now also from the point of view of the momentum wave, because now we don't know what is the spreading of the momentum wave. So if it's related to the wavelength of the De Broglie wave, then we can consider the smaller, the higher is the voltage, the more narrow is then the spreading. And that could explain this. That could explain this experiment. But that's only first idea of the thing. So, I can send you the copy of the because I was not. It's so far from my comfort area that I didn't go into details in trying to understand that, but I tried to set the question and possibly to find experimental things to let nature decide which is correct way of describing the double slit experiment. So I leave the question open. But as you notice, there's much in common in the DU approach and the Bohmian approach in the sense that we have cleared the trajectories. The particle itself may choose any one of the slits, and the momentum wave either fills is spread enough, far enough to pass the both slits, or then if not, then following this type of things. So these are the options. Do you think that there would be possibilities with your available, let's say, available test experiments?
I think, well, my first thought is probably not. You know, if you want to, in a way, we have already measured the bone trajectories with those brief measurements.
Yes.
You carried out, they found that the trajectories very similar.
Yeah.
There's still some disagreements about what those experiments actually measure.
Yeah.
And here, you know, I think, yeah, well, the question I was going to ask you was whether, because what I find difficult to understand is, you know, there is no partial differential equation here which tells you which way you're.
Yes.
I don't know how you get your trajectories. I mean, you just assume a straight line.
Yeah. Yeah.
To the screen.
Yeah. 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 Ismo, there you have a question.
Comment. I'm not sure if there is any problem which the view based on, let's say, Bohmian.
Sorry, I can't hear you.
Standard quantum mechanics, it is very obvious what happens when you have the
Paavo. Paavo, this is my distant ear. You can give that to him.
So you can speak with this one here. Speak with that one, I guess. You speak loud, then that will be.
So what I said is that I cannot comment if there is some difficulty from the viewpoint of Bohmian mechanics, but from the viewpoint of standard quantum mechanics,
yes,
there aren't much difficulties to understand what is happening because it's asymmetric double slit, which is very important to notify. And when you have an asymmetric double slit, then the asymmetry acts as a kind of marker, as a kind of detector states, which couples to the electron state. Okay. And then this explains rather nicely and without any problematics why you will find that kind of result, that it's very well localized on the position of the one slit. Similar phenomena happen quite with great clarity in asymmetric Mach-Zehnder interferometers in photonic experiments, that when you have an asymmetry in the beam splitter, it means that you can somehow distinguish the location or the path the quantum system is taking in these systems, or if you want to think differently, you can make predictions where you will find certain measurable interactions in that system, and that's exactly what you would be expecting on the basis of the standard quantum mechanics. So no paradoxes, no problems if you properly use the standard quantum mechanics.
Yeah. I'd like to comment that from the Bohmian point of view.
Yeah, I think that's absolutely right. You know, quantum mechanics always gives you a consistent picture, providing, you know, you take a Bohrian approach. You know, so yeah, I think, well, quantum mechanics is always right, basically, and there's always an explanation. So if you have this asymmetry, then this is also immediately reflected in the Bohm trajectories, because if you have the asymmetry with a higher probability of going through one slit than the other, then, you know, the pattern changes and you don't have that zero line going across the axis of symmetry. Instead, that line begins to tilt downwards. So, you know, you imagine the wave coming from the upper slit is actually spreading, pushing the wave from the bottom slit. And so the Bohm theory always gives exactly the quantum mechanical results. And I think I'd need to know a little bit more about how you calculate or sort of imply your trajectories, because that seems to me a bit of a mystery, because you don't have an equation for it, so I don't know how that happens.
Okay, let's go a little bit further with my slides, because next we are looking the connection with the momentum wave and then the wave function. So, what's the linkage or mass to the Compton wave, the De Broglie wave, and the wave function? So that's what we derived by looking at the Doppler-shifted Compton waves, which formed the mass wave moving at velocity. When studied like a wave moving at c or wave moving like v, we get these wave numbers here. And if we compare that with Schrödinger's equation for simple case for equation for free particle moving at velocity v, we can now compare. We need to compare these wave numbers here. Next, what we do, we utilize the intrinsic Planck constant here, and apply the Newtonian kinetic energy here, which is the energy in Schrödinger equation here, and we can find out that the result is exactly the same as what we got here. That's very interesting results, because it's we can find that the wave function corresponds to the mass wave, De Broglie wave, carrying the momentum of the object. And once we have the wave carrying the momentum, we then also have the interaction of the interference, which has a component to perpendicular to the beam. That's something to be studied further. Also, it's nice to remember that when we receive a wave, we can't know whether it's a short wave coming at a low velocity, or it's a long wave coming with a high velocity. We only detect the frequency. Okay. Let's say what the mass wave concept meant in describing the energy state, and the simplest we simply take the simplest case, which is the hydrogen atom, and we apply resonance. We require resonance condition here. So the resonance conditions, which means that the number of waves in the electron orbit is now expressed in the form of wave number n divided by r. So that's our momentum, which means that the total energy comprising the kinetic energy, relativistic form, or kinetic energy of the du form of the kinetic energy. And now for comfort, we can use the Colombian energy, applying sorry, you don't have that number here, Colombian energy in form of fine structure constant and the intrinsic Planck constant here. And the result is here. So the energy fulfilling the resonance condition is continuous for each n here. But what is interesting then is that the minimum of the allowed energy states are exactly the principal energy state of hydrogen atoms, which we can get as a Schrödinger energy eigenvalues. And my background is in electron physics, semiconductor physics, so that it's quite natural to consider continuous energy bands, not only in crystal materials, but also when you go into details at atomic level. Philosophically, this is very, very interesting because now energy is not quantized. So, but we can find that the states where we find the minimum, they are quantized. So philosophically, it makes a very big difference. Okay. So we are now facing a possible paradigm shift again. So that mass is not, in this framework, mass is not a form of energy, but a wave-like energy carrier. And we could find in a very concrete way how the wave property of mass can be concluded without any new physics, in fact. It's only a new way of applying the existing physics. And this is very much the same for the old DU approach. Basically, there is no new physics. There's only a new way of building up the package of the components which we have known for a long time. And the mass wave concept allows a physical interpretation, and that's a very important point of the approach, of a quantum of radiation, which means that it's the amount of energy injected by one electron transition into one cycle of electromagnetic radiation. And if we go back to the antenna solution, why did I choose the dipole length equal to one wavelength? In one cycle, the line element in relativity framework is exactly in one cycle, it's one wavelength. And in the DU framework, it's the distance the particle travels during one cycle. And why it's close to one, roughly one, which meant an isotropic antenna, because now our dipole is in the fourth dimension, so it equally radiates into all free space dimensions. But on the same time, it's very easy to understand why small items like a hydrogen atom can emit 21 centimeter emission wavelength, because it works like a 21 centimeter antenna in the fourth dimension, any point source. As a let's say practical aspect of the explanation. So we also found out that we can derive De Broglie wave from Compton wave. Also, we can have a very close connection, and we can even consider that the wave function can be understood as the momentum wave. And particle as a standing wave is a standing wave structure offering a novel interpretation to the wave-particle duality. I'd like to one more time bring up now let's say general level comparison, what we have been done in looking for a holistic perspective for describing physics in general. What are the essential selections here? The essential selection is we have the basic definition, which for very understandable historical reasons are first started from force as the basic unit, which means that energy is a derived quantity, which finally was understood only for 150 years ago, not before that. Although Leibniz found it in principle, but still called it the force. Okay. In dynamic universe, first of all, this is very important. We have mass, which has the Fein property, and instead of defining force as the basic unit, we define energy as a basic unit. And the key question here is that in the case of energy, we can follow the conservation laws. force is a local phenomenon. So we can make equations for balance of forces, but not for conservation of forces, not in the same way as we do for energy. And the consequences is dramatic. The historical path has led to a large number of new postulates, starting from energy balance and zero energy balance. We can practically derive, first of all, cosmology, which goes through Kepler's celestial mechanics, corrected with general relativity, and then to cosmology through equivalence principle. But here we have clear geometry in our space, and we can derive cosmological predictions directly, which leads to very simple algebraic predictions which match extremely well with the observation, and also show the connection between local and the rest of space, which was very essential also for understanding some of the JWST telescope for the behavior of angular size of distant object. And also what's now important is that we can return the understandable way of looking time and distance, so that for human comprehension it's important to understand that events and objects they appear at certain time somewhere. We need the answers to the questions what, where, and when. And in my thinking, that has been the leading motivation for going to find a way of finding an understandable way of looking at the physical phenomena. So we are not changing, as yesterday stated, we are not changing the reality, but we are trying to change the observer-oriented way of building the description, which is the way in relativity theory. It's relativity between observer and the object. In dynamic universe, relativity is primarily the relativity between local and the rest of space. And the way it can be concretely made was what I showed yesterday, was we can build up the system of nested energy frames, which shows what kind of conversions are possible in order to maintain the zero energy balance from the space as whole to local systems and particles, finally coming to the quantum mechanical expressions. And that's where we are. We have very little need for specific additional postulates. And if we are looking for unified theory, a basic demand for unified theory is that the theory shall be based on the same postulate basis. If we have different areas, branches in physics which have different postulate spaces, there's no way of looking at unification. We can of course develop conversion factors or functions to go from one framework to another, but the target should be to have a framework in common where we can describe all areas of physics from the same basis, and that's the idea. But then what we need is, of course, I thank the audience, but I'm also looking for near future to get more resources for finding out, to make the necessary homework to finalize and find out how far we can go with this line, and is it really possible to have a unified framework where all parts can be understood. So thank you very much indeed.
Okay, thank you. We could have, of course, some questions, but maybe we could also move to the panel because that's where we can be discussing. And we have 5 chairs and 6 panelists, but we will solve that somehow. Yeah, sure, go. Yeah, just take it in the meantime. I will set up.
Yeah, so I mean, one thing that occurs to me with your approach, which seems quite extraordinary and very innovative, is that one could solve your problems about not having an equation for your waves. So, when you show it going through a slit, how do we know that it diffracts? But you don't have a wave equation, so we don't know that. But what you could do is just take your geometry and then add the Schrödinger equation on your geometry. And so, you would then have the Bohm trajectories would be in your picture as well, because you would just take the Schrödinger equation with its Bohm interpretation and sort of put that on your geometry. Yeah. So that would be one sort of completion of your theory, because I mean the thing is, what I don't understand is when you draw your trajectory from the upper slit, down to one of the interference maxima, how do you know that that's the path that your particle would take?
We should understand that. I should have the microphone's connection here. Okay, it should be understood more like a conceptual level, which I have achieved here. So that's the interference patterns is something. Well, I think that's called Fraunhofer interference. So that I haven't made any calculations.
So are you thinking of a classical wave equation?
It's more, it's very classical. So that was in my mind when drawing the trajectories, that it follows the classical interface. So there was nothing new.
Anyone else for a quick question here? Yeah.
I'm only building the puzzle from the well-known parts here.
Hi, thank you so much for this talk. So one question, I don't know whether quick or not, but is what shall okay, yeah. So what about the unification with all the other forces?
I'm
unification.
Sorry for my hearing. The acoustic is such that it's very, very difficult with the hearing aid. But I have my distant ear with me, so that when having that with the speaker, then I hear the speaker in my head.
So the question is, what about the other forces and the unification of the other forces? It works all the way long as without any specific.
Sorry, so what kind of forces?
All other forces.
All other forces.
Meaning from the strong to the electroweak, etc.
Okay. So that this is
how the EU works with this.
Interesting question, because as I stated, I have based the whole theory on following the conservation of energy and force. I defined force as the gradient of local potential energy or change or in the momentum. So that's my definition of force. And for example, it has very big consequences, of course, because in present theory, the effect of gravitation is assumed to propagate at the velocity of light. If we look the potential approach, it means that all mass results in any mass, even mass particles, are followed by gravitational potential around them, and any particle then senses the local potential, gravitational potential created by all the other mass. And then it senses, it must move a little bit to find out what is the way of gaining more, of releasing more of the energy. And the ball falls, what is the way down to the valley rather than sideward. So that in that sense I look force as a local phenomenon.
And then I guess the interesting question would be in the case of the quantum potential energy, which is supposed to be, in some ways people talk about that's a-local or non-local or global, because you can derive the force from the quantum potential, right, like Peter Holland does it. But then, right, that's right, the gradient, but then will the quantum potential be a different kind of energy from the way Tuomo thinks about energy?
Yeah, I was more classical. May I add one to the force and gravitational things? Well, yesterday we looked the mechanism that created the inertia, so that we found that inertia is the work we do against the gravitation from the rest of space. But most of the mass in the rest of space is billions of years back. So how could it propagate to result the inertia in our local phenomena? It doesn't work that way. No. Also in dynamic universe, when we follow the energy balance, it turns out that the velocity of the expansion is at the same time the satellite velocity in the expanding system. So the only acceptable velocity for carrying energy is the velocity c. That comes from the same basic equation, the energy balance. And that's why now also a mass particle moving, it doesn't interfere this, because inside the resonator is still only the mass, the energy is expressed through the velocity of light, not through the velocity of the moment. And the momentum follows the moving particle. And that makes a very big difference, that in experiments and what we solve also in the double slit is the momentum wave. And with high acceleration voltages, it means that it carries most of the energy. There's less energy than running in the resonator that follows the trajectory determined by the momentum wave.